we would like to obtain the sum of these two numbers using the 2's complement addition in an 8-bit scheme. So how do we do that? We know we can represent 64 as 2 to the power 6, and therefore this is equivalent to 1000. These are the powers of 2, and therefore this is how you would represent 64. And 58, you would simply represent it with 32 plus 16, 48, plus 10, this is plus 8, and plus 2, this becomes like that. So this is equivalent to 58. So if you are to do the summation using the 2's complement addition in 8-bit scheme, all you need to do is perform this as they are, and we make sure that the most significant bit is a 0 in either case. We can see that these are 4 plus 0 here becomes 8 bits, and this becomes 8 bits. That is the requirement we are given, that we are operating in 8-bit scheme, and for that reason we perform the normal addition. This becomes 0 1 0 1 1 1 1 0. So as we can see, there is no overflow bit. These are also in the 8-bit scheme, and therefore this should be the answer of this addition or this summation, and this should be equivalent to 122. And I believe if you evaluate this one, you'll find that that is true. So that is how we perform the summation using the 2's complement method. In the event that the auged and the added are negative, then the sum is going to be negative, and it is going to be in 2's complement form, and we can see that there is going to be some carry bit that is going to be generated, which we are going to see what happens with it. We say that during this addition process, any carry bit that is generated should be discarded. That is the most important. That is the most significant bit. If it exceeds the 8-bit column, the 8-bit scheme that we are using, if you find the 9th bit as the MSB, then you normally discard the most significant bit. The magnitude of the negative sum can be determined by obtaining the 2's complement of the addition result, and the best way to understand that is by an example. And in this example, we are going to do summation of a negative number or two negative numbers. So we want to obtain the sum of minus 39 and minus 57 using the 2's complement notation. So how we do that is simply to represent the minus 39 using the binary notation, which we know that is going to be given by 32 plus 4 plus 3 plus 1. This becomes 1 0 0 because of 16 and 8, then 1 this is supposed to have been 2, 4 2 1 that. So this is the binary representation of 39, and if you are using the 8-bit scheme, what we would need to do is to add two numbers, 2 zeros preceding our magnitude, and then we obtain the ones complement or the 2's complement, which means you're going to take the left bits to the least significant 1 bit, and so therefore this remains as 1. All the others are complemented, so we have 0 0 1 1 1 1. So this is the minus 39 in 2's complement form, and then we can do the same for 57 or minus 57 in 2's complement. And if you just follow the procedure that we have come up with, we know that it is going to be 1 1 0 0 0 1 1 1, and this one is the 2's complement of form of minus 57. So if you are now to do the summation, what we need to do is to just add these two. So this is minus 57. I bring this one here to become 1 1. So I now perform the addition, and when I perform the addition, the answer will be 2's complement form. That is a very important aspect. So let's do this addition. This is 1 plus 1, 0 carry 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 1, 1, 0 carry 1, 1 1. 1 plus 1 plus 1 in binary is going to be 1 1. So that is the one I was trying to figure out. Therefore this becomes the final solution because we have already discarded this one. And therefore, if you are now to find the final answer, which we have seen that this is already in 2's complement. First and foremost, this is the final answer, but we cannot understand this final answer unless we first of all convert it to the normal binary so that we can see what it represents. And for us to do that, we would need to follow the same procedure that we follow forming the 2's complement. That is, look for the least significant 1 bit and then complement to the left, the bits to the left of that LSB 1 bit, and therefore we are going to find that these two are going to be complemented to become 101. The others remains as such. So this one is supposed to be 100. And now if we are to convert this back to decimal, you would find that this is equivalent to, this is 64, that 2. And whatever, when you add these two, they tell you that this number is equivalent to 96. And since we know that our two numbers were both negative, therefore we know that when you add these two, they are going to give you a positive number of 96 if you ignore the negative signs. But for us to represent this negative sign in 2's complement, this number represents the 2's complement of 96. So this number is equivalent to negative 96. So that is the final answer for that lathering the procedure. So we observe that the subtraction process is equivalent to the one that we have done of the addition of a positive number and a negative number, and we just need to let the positive number remain unchanged. So it will remain in the binary number notation, and negative number you will change it to the 2's complement notation. If the difference between the two numbers is negative, then the binary sequence obtained will be the 2's complement. Otherwise, it will be in the normal binary form. So when it is in the 2's complement notation, the most significant bit will be a 1. On the other hand, a positive difference will have a most significant bit being 0, and the magnitude is going to be directly binary notation form without needing to convert it back from the 2's complement. We'll need to do an example for that, and we want to say now that we want to do a subtraction of two numbers. We want to have two numbers, and in this case we're going to have 82 minus 27. So our 82 is we are writing it in this form, 82 minus 27. In that case, this is our positive number and this is our negative number. Therefore, we can write it as a summation of 82 plus negative 27. That is very basic mathematics. Therefore, what we need to do is that 82, we can express it as in binary form as equivalent to 64 plus 16 plus 2, which is equivalent to 1, 32 is 0, 16, 8 is 0, 4 is 0, 2 is 1, and 1 is 0. So this is equivalent to 82, but we need to express it in the 8-bit notation. Therefore, we add a 0 to the left so that we are sure that the number has a 0 as its most significant bit. The other number is 27. We won't write it in the negative format. We can express it first as a positive number, which we are going to say is equal to negative 16 plus 8 plus 3, and 3 is equivalent to 2 plus 1. So in this case, we are going to have 1, 1, 1, 1. Oh yeah, there's one that I missed out, which is 4. So 4 is right here. So that is how you write 27 in binary form. So if you are to express it as a negative number, we use the 2's complement form. And before we do that change, we must make sure that it is in 8-bit notation. We express this one as positive 27. So for us to get the 2's complement, we just leave the least significant 1 bit unchanged and we complement all the others. And therefore we are going to have 1, 1, 1, 0, 0, 1, 0. And this one remains unchanged. So this is the negative 27 in 2's complement form. And therefore, for us to perform the addition, what we simply need is to add this 2's complement form of 27 and the normal representation of 82, which becomes as follows. So these are the two numbers that I am going to do the normal addition, and I add now. This becomes 1. Again, this becomes our summation, and we have an overflow bit, which, as the rules say, we discard. And now the final answer should be 0011 0111, and this number is equivalent to 55 in decimal notation, and this is a positive 55. So that example should be adequate to illustrate how we can perform signed binary arithmetic using 2's complement notation.